Welcome to Lesson 3.2, Part 2. We're going to start off with a little vocabulary first. What does it mean to extrapolate or extrapolation? It is using a regression line to predict far outside the interval of values of the explanatory variables x. These predictions are often not accurate. Now we're going to switch to regression lines. A good regression line makes the vertical distance of the points from the line as small as possible. And how do we create an equation of a least square line? Well, we do know from the previous notes that the slope-intercept form of a least square line is much like our slope-intercept form in Algebra 1. It's y hat, the predicted value of y, equals a plus bx, where a is equal to your y-intercept and b is equal to your slope. So we're going to actually find out how to get our a and b values. Well, b, or the slope, is equal to the correlation r times s sub y divided by s sub x. And what is s sub y? Well, that is the standard deviation of y and the standard deviation of x. And a, our y-intercept, is equal to the mean of y, or y bar, minus b, our slope, times x bar, or the mean of x. Well, where do we get these values for s sub y, s sub x, y bar, and x bar? We're going to let the calculator do the work for us. So in class, we will calculate the standard deviation of y, the standard deviation of x, our correlation, our mean of y, and our mean of x, and then we'll be able to plug them into these two equations to solve for a and b, getting our equation of a least square line. Okay, the slope equation tells us that a change of one standard deviation in x corresponds to a change of r standard deviations in y. When the variables are perfectly correlated, when r equals 1 or r equals negative 1, the change in y hat is the same as a change in x. Remember that looks like y hat. Right. In standard deviation units. Now, as the correlation grows less strong, as the values of r get further and further away from 1 and negative 1, y hat moves less in response to change in x. Well, what does that mean? That means if our two variables are not that strongly linear related in a linear way, then when x changes, y progressively responds less to that change in x. How well the line fits the data. The first principles of data analysis. We need to look at the overall pattern and look for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship. We see departures by looking at the residuals. Because the residuals show how far the data falls from the regression line, looking at the residuals helps us see how well the line describes the data. Residuals, special properties. The mean of the least square residuals is always 0. Positive and negative residuals cancel each other out. The residual is the average prediction error. Residual plots turn the regression line horizontal. They magnify the deviations or distance from the line of the points from the line. There should be no pattern. If the residual plot has a curved pattern, a linear regression model is not appropriate for this data. Standard deviation of residuals. They tell us how far off the predictions are, on average. So how do we find the standard deviation of the residuals? We will use the equation, the standard deviation of the residuals, s equals the square root of the sum of all the residuals squared divided by n minus 2. And if you remember, this looks a lot like the standard deviation we did in chapter 1. But why are we dividing by n minus 2 versus n minus 1? Well, we will actually see that in chapter 12. we can even simplify this a little more and do the standard deviation equals the square root, the sum of each individual y value minus the predicted value, or y hat, squared, divided by n minus 2. Now this value gives us the approximate size of the typical or average prediction error, residual. The role of R-squared in regression. Residual plots tells us how well the regression line fits the data. Standard deviation gives us a numerical estimate of the average size of our prediction errors. And R-squared tells us how well the least square line predicts values of the response variable y. R-squared is called the coefficient of determination. And there is an equation that will allow us to find R-squared. It's made up of some terms that we need to go over. SSE stands for the sum of squared errors. And that is calculated by finding the sum of all your residuals squared. And SST, which is the total variation in y values, and that is found by finding the sum of all your individual y's minus y bar, or the mean of y squared. Okay, now that we know those two pieces, we can go ahead and give you the equation of r squared, which is r squared equals 1 minus SSE divided by SST. Coefficient of determination, R squared in regression, is the fraction of variation in the values of y that is accounted for by the least square regression line of y on x. Important. Distinction of the explanatory and response variables is important. If you switch the variables, you will get a different regression line. Correlation and regression lines describe only linear relationships. Always plot your data because residual plots show or not show a linear relationship. And I'm going to add another one. Association does not imply causation. Association does not imply causation. Thank you for joining me for Lesson 3.2, Part 2.